Hello everyone, and thank you for attending this seminar on the research project Life Cycle Assessment of Colombian cocoa pod has transformation into value-added products. The cocoa production is an important activity for the economic development of the agro-industrial sector in Colombia, and this activity generates agricultural residues, of course. The highest volume of residues from cocoa is derived mainly from the shells known as cocoa pod hulls, which will be called CPH, representing between 65 to 75% of the fruit's weight. The physicochemical characterization of CPH reveals its promising potential to produce activated carbon, potassium hydroxide, and cellulose. In this project, the activated carbon was obtained through pyrolysis employing potassium hydroxide as the activating agent. For potassium hydroxide, this was obtained by ash leaching from CPH followed by gasification. And finally, for cellulose was obtained using alkaline treatment and autohydrolysis. As a result of the life cycle assessment conduct, it was found that the production of potassium hydroxide showed the best environmental performance with the low impact, followed by cellulose obtained through autohydrolysis, cellulose obtained through alkaline treatment, and finally the activated carbon. Across all transformation processes, the categories with the most significant impact are global warming potential and terrestrial ecotoxicity potential, with electricity consumption during the transformation process emerging as the primary contributor to the life cycle assessment results. Additionally, the CPH itself plays a significant role in the freshwater eutrophication potential impact attributed to the release of mineral nutrients that ultimately leach into water bodies. The solar drain was considered for CPH pretreatment, and under this scenario, the impact quantification significantly decreased, with cellulose obtained by autohydrolysis shown the grids decreased around 63%, followed by cellulose obtained by alkaline treatment with 54%, potassium hydroxide with 41%, and finally activated carbon with a reduction of 52%. Finally, the value-added products was characterized and it was found that they have favorable properties, making them suitable for various potential applications. Cocoa production in Colombia is one of the most important agro-industrial activities due to its direct impact in the social and economic development of smallholder farmers, many of them located in vulnerable and post-conflict regions. During the last decade, the national cocoa production has increased significantly, and based on 2022 production data, the departments with the highest participation in the cocoa production are Santander, Arauca, Antioquia, Tolima, Huila, and Nariño. The Theobroma cocoa tree is a species of the Malvaceae family, and botanically the cocoa is considered very like a fruit. The cocoa trees develops well in relatively warm climate and relatively high humidity. Generally speaking, there are three varieties of cocoa. There are Criollo, Forastero, and Trinitario. And the cocoa fruit consists of three main parts: the cocoa beans, the mucilage, and the cocoa pod husk. And the CPH is the external part of the fruit, and it represents between 65 to 75% of dry weight of the fruit. Previously, various evaluations have been conducted regarding the utilization of CPH to obtain a range of products, including energy. And considering that there are many ways for the utilization of CPH, the application of the life cycle cell analysis methodology serves as a valuable tool for assessing and comparing the environmental performance of this transformation process. The LCA has not been used to assess the post-haste transformation of Colombian cocoa into value-added products such as caustic potash, activated carbon, and cellulose, which is the objective of this project. Show you some of the alternatives of use of CPH. These alternatives include the use of CPH to produce bioenergy through thermochemical processes such as combustion, gasification, pyrolysis, and hydrothermal carbonization to produce biogas by anaerobic digestion is a biochemical conversion as a catalyst support due to its potassium oxide content for the transesterification in the production of biodiesel from vegetable oil, as a binder material for pellets for the production of biochar, of activated carbon by its amount of its carbon, for the production of potassium hydroxide and carbonate due to its high potassium content, as a source for the extraction of antioxidants like vitamin C and theobromine, the extraction of protein, alimentary fiber, lignocellulosic components, and pectin, among others. The life cycle assessment methodology considers the guidelines of the standard ISO 14040, and it is a useful tool to assess the environmental performance of products and processes. LCA consists of the determination and evaluation of the inputs, outputs, and the potential environmental impact of a product system or technologies through its life cycles. The LCA methodology comprising 4 phases, and these phases constantly feedback. The first consists of defining the goal and scope, and in this phase it provides the outline and guidance for the study and include the functional unit, the system boundary, geographic location of the study, assumptions and limitation, allocation options based on mass energy on or economic methods, impacts categories, data source, and requirement. The second is the inventory analysis, where the consumption of resource and generation of quantities of emission, waste, and energy for the analysis are estimates. Then, the life cycle impact assessment is carried out, and the LCA aims to evaluate the magnitude and significance of the potential environmental impacts associated with impact categories and category indicators. And these finally correspond to the interpretation of the results of LCA. For the goal and scope definition, the LCA could be defined with different approach. This could be gate to gate, cradle to gate, cradle to grape, or cradle to cradle. Gate to gate considers only the design and production process in whole production chains. Cradle to gate considered from material extraction to the factory gate. Cradle to gate is the complete LCA from material extraction through production process, distribution, use, and final disposal stage, including related transport. And cradle to cradle considers the complete LCA and admits the recovery or and recycling of the outputs of the waste disposal of the system. The general objective of this research was to determine the environmental performance to produce caustic potash, activated carbon, and cellulose from Colombian cocoa pod husk using LCA methodology. And to achieve this objective, the following specific objectives have to be fulfilled. First, to perform the inventory analysis of processes involved in the generation of CPH and its transformation to produce caustic potash, activated carbon, and cellulose. Second, to quantify the environmental impact categories using the LCA methodology to produce caustic potash, activated carbon, and cellulose from CPH. And finally, to identify the hotspots of the environmental assessment for each of the analyzed transformation process of CPH and propose alternatives for improvement that could be evaluated in future works. For the methodology, the aim of this study was to assess the environmental performance of utilizing CPH to produce caustic potash, activated carbon, and cellulose. The work adopts a cradle-to-gate approach. The data of production of organic cocoa system was obtained from 10 agroforestry farms of the Asociación Héroes del Cultivo in the rural zone of San Bernardo Ibagué. The functional unit was 1 kg of CPH. The allocation procedure was on a mass basis. The data source include primary and secondary data. The primary data collected from field survey of cocoa farmers carried out in the period of April to October 2022 in the rural zone of San Bernardo Ibagué. Additional secondary data obtained from Equinven and Agro Footprint database were carried for support this research. And for transformation of CPH into the products, laboratory tests were carried out to obtain primary data for mass and energy balance and waste generation. The LCA was performed with the CIMAPRO software, the Equinven and Agri Footprint database, and the receipt midpoint method for impact assessment. The midpoint impact categories used for this research were climate change, human toxicity, cancer, terrestrial acidification, freshwater eutrophication, terrestrial ecotoxicity, freshwater ecotoxicity, marine ecotoxicity, water use, mineral resource scarcity, fossil resource scarcity, with the respective characterization factors and units. The system boundaries for each system were: for organic cocoa production, start with nursery and ends with the packing of dry cocoa beans. For this system, the inputs were supermagro and lime water, gas oil, and jute bag, and the outputs were local emissions, CPH, mucilage, and dry cocoa beans. This was necessary to obtain the impact associated with the generation of CPH, which is necessary to develop the LCA or use the CPH to obtain these products. Then, for the activated carbon production, start with drying and grinding of CPH, which correspond to the pre-treatment of CPH, and ends with the drying of activated carbon. For this system, the input were energy, CPH, potassium hydroxide, water, nitrogen, and hydrochloric acid. And the output were local emission, liquid weights, and activated carbon. For the production of potassium hydroxide, start with the pretreatment of the CPH and ends with the evaporation stage to obtain the solid products. The input for this system were energy, CPH, water, calcium hydroxide, and the output of the system were local emissions, solid weights, calcium carbonate, and the product potassium hydroxide. For the cellulose, this was obtained using two methodologies. The first was alkaline treatment. For this process starts with the CPH pretreatment and ends with the drying of the cellulose. The input were energy, the CPH, sodium hydroxide, and water, and the output were local emission, liquid waste, and cellulose. For cellulose production by autohydrolysis, start with the pretreatment of CPH and ends with the drying of the cellulose. The input for this system were energy, CPH, water, and the output were local emission, liquid weights, and cellulose. The assumption and limitation of this research correspond to: first, for the analysis of the organic cocoa production, the first 4 years from cultivation were considered as the established phase of the cocoa crop to start producing cocoa pod. This was considered to develop the inventory analysis of this system when I obtained the impact related with the generation of CPH. For the life cycle inventory analysis, irrigation for the cacao production was not included because the precipitation of the geographic location of the study is known for the development of the crop. And for the LCA, the impact analysis, the transformation process of CPH were assumed to take place in the rural zone of San Bernardo y Ibagué, so no type of transportation was considered. The life cycle inventory analysis was carried out considering all the stages for each system, for each process, and also the input and output for each stage in the process. For the organic cocoa production, the data correspond to the amount of raw material from the technosphere. This was a primary data taken from Robinson Tapiero, the association leader. The data for raw material production was a secondary data taken from database. The number of resources from nature correspond to secondary data taken from IDEAN information. The data for resource use correspond to secondary data taken from database, and the amount of product, co-product, and biowaste generated correspond to primary data taken from the interview of Robinson Tapiero. For the carbon production process, the amount of raw material corresponds to the potassium hydroxide, ionized water, hydrochloric acid, and the CPH were primary data taken from the laboratory scale process. The data for these raw materials were secondary data taken from the database. The number of resource and energy used for the process were primary data taken from the laboratory scale process and equipment specification. The data for resource and energy were secondary data taken from equipment database, and the amount of product and waste generated, which correspond to activated carbon and liquid waste, were primary data taken from the laboratory scale process. For the potassium hydroxide production, the amount of raw material from the technosphere corresponds to the CPH, deionized water, and calcium hydroxide were primary data taken from the laboratory scale process. The data for these raw materials were secondary data taken from the database. The number of resources and energy used for this transformation process were primary data taken from the laboratory scale process and equipment specification. The data for this resource and energy use were secondary data taken from the equipment database. The amount of product and waste generated correspond to the potassium hydroxide and the solid waste were primary data and were taken from the laboratory scale process. For the cellulose production process through alkaline treatment, the amount of raw material from the technosphere corresponds to CPH, sodium hydroxide, the ionized water, were primary data taken from laboratory scale process. The data for these raw materials were secondary data taken from database. The number of resources and energy used for this transformation process were primary data taken from laboratory scale process and equipment specification. The data for the energy used were secondary data taken from the equipment database, and the amount of product and waste generated correspond to the cellulose and the liquid waste were primary data taken from the laboratory scale process. Finally, for the cellulose production process through autohydrolysis, the amount of raw material correspond to the CPH and deionized water were primary data taken from the laboratory scale process. The data for this raw material were secondary data taken from database. The number of energy used for this transformation were primary data taken from laboratory scale process and equipment and specification. The data for this energy use were secondary data taken from equipment database, and the amount of product and waste generated correspond to the cellulose and liquid waste were primary data taken from laboratory scale process. As I mentioned, 10 impact categories were evaluated, and the outcome of this interpretation phase corresponds to the conclusion and recommendation of the study carried out. In the interpretation, it is intended first to assess the environmental performance to produce caustic, potash, activated carbon, and cellulose from CPH, and second, to identify the source of the environmental issues for each of the analyzed transformation process of CPH and propose alternatives for improvement in future work. The first results correspond to the cocoa output as characterization. In the physical analysis, the most relevant parameters are the relation of CPH with respect to dry cocoa beans, which is around 10, and the CPH moisture, which is 85.5%. And in this figure, we can see the physical relationship between the cocoa beans, which is what currently has valued and is used in the chocolate industry, the mucilage, this part that covers the cocoa beans, and the external pulp, the CPH, which is the largest part of the fruit. For the physicochemical characterization of CPH was determined the parameters on dry matter basis. The moisture was 3.6%, the volatile matter was 72.9%, the ash was 8.5%, the fixed carbon was 15%, the hemicellulose was 52.1%, the cellulose was 23.7%, the lignin was 16.5%, and the potassium was 2,795 milligrams per 100 grams. Also, a CEDX semi-quantitative analysis was carried out for the CPH and its ashes. For the CPH, we can see an important content of carbon, and over the ashes, we can see an important content of potassium. Over the figure 15 correspond to the CPH, we can see a rigid and fibrous structure which is characteristic of lignocellulose components. And over the figure 16, we can see the CPH ashes images which correspond to a heterogeneous surface with some non-uniform porosity. In the life cycle inventory analysis results, the amounts of inputs and outputs were obtained for each of the process analyses. In this table 10, we can see the result correspond to the organic cocoa production. The table 11 shows the results of the amounts of inputs and outputs to produce activated carbon from CPH. The table 12 shows the results of the amounts of inputs and outputs to produce potassium hydroxide from CPH. The table 13 and 14 shows the results of amounts of inputs and outputs to produce cellulose by alkaline treatment, how we can see here, and to produce cellulose by autohydrolysis process. The first life cycle impact assessment corresponds to the organic cocoa production with different allocation procedure. This means that the process was evaluated with two scenarios. One where 1 kilogram of CPH is disposed in open field, and the other where the same amount of CPH is used as a co-product. The table shows that when the CPH is disposed of in open field and is considered as bio-waste, the environmental impact increases for all evaluated categories. And the categories that exhibit a significant difference between these two scenarios are the climate change, the human toxicity cancer, the terrestrial acidification, the terrestrial ecotoxicity, the freshwater ecotoxicity, and the marine ecotoxicity. The other categories have the least difference between these scenarios evaluated. The life cycle impact assessment contribution shows that for both evaluated scenarios, the bio-waste is the main contribution to the global warming potential impact. When the biowaste degradation occurs, resulting in the production of greenhouse gases, primarily carbon dioxide and methane. The biowaste also contributes to the health toxicity potential cancer, mainly through its heavy metal and dioxin emissions. The biowaste degradation also generates leachates that cause soil alterations such as acidification, and these leachates eventually end up into bodies of water, leading to adverse effects including eutrophication and ecotoxicity in both freshwater water and marine water. When CPH is not included as part of the biowaste generated during organic cocoa production, its contribution decreases in the impact category as the amount of biowaste significantly reduces. In organic farming practice, the use of lime during the vegetative growth stage is common. The lime is the clear green. So this process contributes significantly to some impacts how we can see here. The human toxicity, the terrestrial acidification, the terrestrial ecotoxicity, freshwater and marine ecotoxicity, and even more to the mineral resource scarcity due to the mining extraction required to produce the lime. And to produce organic cocoa, the pest and weed control is performed mechanically with chainsaw. As a result, the gasoil used for the equipment is an important contributor in certain impact categories, how we can see here, particularly to the terrestrial acidification, the human toxicity potential cancer, and even more over the fossil scarcity potential. The life cycle impact assessment result of the CPH transformation into value-added products using an oven in the predetermination of the CPH is shown in this table. Why I do this acceleration? Because for this analysis we consider two options for the predetermination of the CPH. The first option is the CPH is dried in an oven in the laboratory, and the other corresponds to the solar drying of CPH. For these scenarios with the predetermination of CPH using an oven in the laboratory, in general terms, the production of activated carbon has a greater impact in all evaluated categories due to the high energy and resource requirements for this process, compared to the production of potassium hydroxide and the cellulose production. Respect to the general environmental impacts, the production of cellulose is in second place, and finally the production of potassium hydroxide is the last process that generates less impact. How I mentioned, consider that the solar drying for CPH can be carried out without affecting the other stage of the transformation process. The life cycle impact assessment results correspond to these scenarios shown in this table. When solar drying is considered for the predetermination of CPH, the impact quantification significantly decreases, with the cellulose obtained by autohydrolysis showing the decrease around 63%, followed by cellulose obtained by alkaline triamine with 54%, the potassium hydroxide with 41%, and finally activated carbon with a reduction of 52%. It is observed that the drying pretreatment stage of CPH done in laboratory is the primary factor contribution to the impact quantification on cellulose production through autohydrolysis. In addition, it has a significant impact on the other products. The table shows that potassium hydroxide and cellulose production have similar environmental performance under this analysis condition. The contribution of the inputs and outputs to produce activated carbon was analyzed considering the use of an oven in the pretreatment of the CPH step and the scenario of using solar drying. It is observed that for both drying options using the CPH pretreatment, the total electricity consumption required for the transformation process is the most significant contribution factor in all the categories evaluated, with values exceeding, how we can see here, 90% and 50% for fresh water eutrophication. For the fresh water eutrophication category, how we can see here, there is a notable contribution of CPH, and this contribution is due to the nutrients and minerals that eventually end up in water bodies during cocoa production, where the CPH is generated. For the potassium hydroxide, both scenarios for the pretreatment of CPH were considered. This figure corresponds to the result with pretreatment drying of CPH in an oven in the laboratory, and this corresponds using solar drying pretreatment. It is observed that for this scenario, the total electricity consumption required for the transformation process with drying of CPH in a laboratory oven is the primary contributing factor for all evaluated categories, with values mostly exceeding 90% except for the fresh water eutrophication category with a contribution of 56.22%. When the solar drying is considered, the gates difference in electricity contribution is found in the freshwater eutrophication impact, when the CPH is important for this category under this condition. The LCA contribution results to produce unbleached cellulose by alkaline and autohydrolysis methodology shows a similar trend to that observed in the preceding section for potassium hydroxide production. The total electricity consumption required for the transformation process is the most significant contribution factor in all categories evaluated. When comparing the process with pretreatment drying using an oven and laboratory and the solar drying, the most significant difference in electricity contribution for cellulose is observed in freshwater eutrophication impact category with a maximum variation of 20%.